Good morning, everyone. So today we are going to continue with the atomic models discussion. Okay. So as I already told you in the last class that in this class we are going to talk about the alpha particle scattering experiment. Okay. So Sir Ernst Rutherford, okay, was the one who supervised the experiment. Okay. And his associate and student were the ones to actually conduct this experiment. So let us quickly jump into the experimental facts and not on the history. Okay. Alpha particle scattering. So you understand that it involves alpha particle. Okay, now alpha particle means it is helium nucleus, which means helium has atomic number 2, right? So it will have 2 electrons as well, right? And 2 protons. That is 2 units of negative charge, which we can say -2, okay, and 2 unit of positive charge. So when we say helium nucleus, you understand that it only consists of this part, that is no electrons. So helium nucleus means it will have only the +2 charge, no -2, which means alpha particle is nothing but helium 2 plus, okay, 2 unit of positive charge. So it is a positively charged particle. Now what is scattering? Scattering means changing the path. Okay, so you can understand that alpha particle will get scattered. That is, it will move initially in one direction and it will change its path. That is in this direction, say. Okay, initially in this direction, but it will change its path. On what? It's not going to change its path without any reason, right? There has to be something that will actually force it to change its path. Okay, so this was the actual concept of the experiment. Now let us look at the experimental setup. Okay, so we will have a source of alpha particle. Source means the material or the element that is going to give out the alpha particle. Okay, in the experiment, bismuth 214 was the source of the alpha particle. Okay, this was the source. So the source is kept in a lead box. Okay, and then alpha particles are ejected out from this source. Okay, also thin lead bricks are arranged in this manner. Why? Because alpha particles are going to be ejected in all directions, right? So in order to focus the direction, that is, we only want the parallel beam. That is why lead bricks are kept on the way, so that they absorb the alpha particles that scatter in random direction. This is going to increase the accuracy of the experiment. So we get only a collimated, a focused beam, as you can see here. Now thin gold foil is also kept. This is the thin gold foil, for example. Okay, this is the thin gold foil, and here this gold foil is actually the source of atom. See, this experiment was conducted to actually study atoms. Okay, so gold here, thin gold foil, is acting as the source of atom. Okay, and obviously detector is also kept. Okay, this is the detector, a circular screen. Okay, all over a circular screen, this part. This circular screen is made of zinc sulfide, and a microscope is also there, that is attached. Okay, so zinc sulfide is actually a material that is going to produce fluorescence. Okay, like this, scintillations, fluorescence, tiny flashes of light. When energetic particles heat the screen, the energy of the particles will induce light flashes, and these light flashes will be detected or counted. Okay, microscope is used to detect these light flashes. Okay, so this was the setup. Now the box here is also enclosed by lead. Okay, lead, L-E-A-D. This is also lead, this is also lead. Same reason, so that the random direction scattered alpha particles are absorbed and the experiment is less errored. Okay, so this was pretty much the setup. Now another thing that you need to note is we have a thin gold foil. Okay, this is a very thin gold foil of the order of 10 to the power -7 meter. Very thin, right? Why? Because we want to reduce the number of atoms. When the foil is thicker, there will be more number of atoms. So it will be difficult to get the conclusion of the experiment, right? So for that, we need a thin foil so that the atoms will be less in number and we can study the interaction of this alpha particle, okay, with the atom, with single atoms. Okay, so this was done. Okay, so now let's talk about the results. Okay, what were the results? So this is the beam of alpha particle. Okay, let us suppose this is the beam of the alpha particle. Here we have the gold foil. Okay, now this is alpha. Okay, now the result, the first point was that most of the alpha particles were undeflected. That is, they did not change their path. Okay, most of the alpha particles did not change their path. They passed through the gold foil. Very few alpha particles, like around 1 in 8,000, were deflected by very small angles. Okay, were deflected by small angles like this. And very few, that is 1 in about a millionth maybe, were actually deflected back. That is, they followed the same path by which they had come, like this. Okay, so they strike the gold foil and returned back. So this is what happened. Most of the alpha particles were undeflected. Okay, few of them actually deflected by small angles. Some deflected by angles that were greater than 90 degree. So what do we mean by that? See, this is the incident direction. This is 90 degree, right? So they deflected more than 90. This is 90 degree, right? So they deflected more than 90, like this. Okay, and very few actually deflected back like this. So you can say the deflection was 180 degree for this path, right? And this was greater than 90 degree. Okay, so these were the three results. Okay, now according to the first model, that is the Thomson's atomic model, it was earlier stated that in an atom the positive charge is uniformly distributed, right? So see, alpha particle is also a positively charged particle. So if that was the case, if alpha particle hits this atom, for example, we have a beam of alpha particle, if positive charge is everywhere, alpha particle should be scattered, right? Uniformly scattered back. But in this case, in the experiment, what was happening? Alpha particle was passing by most of the alpha particle, right? So this actually was a contradiction to the first model. So the first model failed. Thomson's atomic model failed. Okay, that positive charge is uniformly distributed. So the conclusion from this experiment was that in atoms, most of the space is empty, right? Empty. That is why most of the alpha particles were undeflected, right? They were passing through. Okay, now some alpha particles were deflecting back, right? So this indicated that there was a positive charged part in the atom. Okay, a part was there in the atom that was positively charged. Since very few alpha particles were deflecting back, it indicated that the positive charge is very strong, very strong, powerful positive charge, because we know that alpha particle being a positive charge will be deflected by positive charge only, right? So this indicated that there is something in the center. Okay, and since the positive charge is strong enough to actually repel back the alpha particle in the same path, we can conclude that the center of the atom is very dense. Okay, most of the mass is also concentrated in that center. So the conclusions that were made from this model was that since most of the alpha particles pass through the gold foil, so atom consists of mostly empty space. Okay, atom consists of mostly empty space. Okay, since very few alpha particles deflected, okay, by small angles, it concluded that there is existence of positive area, okay, in an atom. Now, since very few, 1 in about a million maybe, alpha particles were scattered back in the same direction, it included that the positive area is somewhere in the center of the atom. Center is positive, okay, and very dense and very powerful. Okay, very dense, very powerful. So according to him, this is an atom, for example, which is mostly empty, and we have a center like this. Okay, the center holds all the positive charges, and the center is very dense, very heavy. Okay, very tiny but very heavy. And since we know that atom is neutral, right? So there will be electrons also present, that is negatively charged subatomic particles. Okay, so according to this model, it was given that electrons are revolving around the nucleus in fixed orbits. This is an electron and it revolves around the nucleus like this. Okay, in fixed orbit. So this is how the model was again composed. Okay, so first model, that is the J.J. Thomson's model, failed here. Second model came. This second model was known as the Rutherford's atomic model. It was also known as the planetary model. Why? Because according to this model, electron is revolving around the nucleus, just like planets revolve around the sun. Okay. Also, Rutherford was the one to discover nucleus. This is known as the nucleus. The central core is known as the nucleus. The central core that holds most of the positive charge. Okay. That is why Rutherford's atomic model, this one here, Rutherford's atomic model is also known as the nuclear model. Okay, so we have Rutherford's atomic model, we have the planetary model and the nuclear model. Okay, so here I'll write it, planetary model. These three are the same thing, no difference. Okay, So you have to remember the names. Okay, sorry, you can't see it, I think, huh? So this is all about the Rutherford's atomic model. This is how the model came, okay, through the experiment, and these were the conclusion about atom. The atomic model of Rutherford gave these conclusions. Along with the fourth conclusion is that electrons are revolving around the nucleus in fixed orbit. Okay, so in the next class, in the next lecture, I will talk about the limitations. First, I will talk about the success of the model, second about the limitation, and then we are going to talk about the third model. Okay, so I hope you actually enjoyed and understood this lecture. So if you have understood and taken something from here, then please don't forget to subscribe to my channel, like and comment. Okay, so yes, and also share this video with your friends so that they also can look at this lecture, watch this lecture and understand something. So okay, meet you again with another video. Bye.